Hi everyone! In this video, I'll be presenting a brand new method to make sky cooling paint using common grocery and hardware store items. This paint is inexpensive, the ingredients are readily available, and most importantly, it stays several degrees below ambient air temperature, even in direct sunlight. What that means is that we can use this paint to make cooling panels, which provide electricity-free air conditioning. In the future, I'll be attempting to build panels to air condition a small tool shed as a scaled-down test, working toward a large-scale practical design that anyone can make at home. That's for another video. The paint itself will give us more than enough to learn about here. The process involves beautifully controlled microscopic crystallization, do-it-yourself plastic recycling, and the intentional misuse of kitchen equipment. Toward the end, I'll go through a simple step-by-step recipe, but first a brief explanation of how this paint works, and then we'll dive into my development process and several discoveries I made along the way. This is my second video about radiative cooling paint, and I think my original explanation was less intuitive than it could have been. Paint of this kind has two essential features. First, it needs to be extremely white so that visible light bounces off of it and is not absorbed as heat. Therefore, it absorbs very little sunlight, which would otherwise warm it up. The other feature is that it must radiate a particular wavelength of infrared light that passes straight through the Earth's atmosphere without being absorbed. All materials emit their heat as infrared light, which is why an infrared camera works. And typically, take note because this part is important, an object will easily absorb the same spectrum of infrared light that it emits. If that spectrum is absorbed by the atmosphere, it means that the atmosphere will, in return, emit the same spectrum of light back toward the Earth, warming all objects that easily absorb that same wavelength. If our paint releases light that does not react with the atmosphere, it will fly directly off into the coldness of outer space. And because the atmosphere does not emit the same wavelength back at the paint, the energy gained versus energy lost does not balance out. The paint gets colder than the air around it. Note that this does not violate any laws of thermodynamics. It only works because outer space is very cold, and heat naturally flows from hot things into cold things. The one feature that makes a cooling paint seem like magic is that it ignores the atmosphere, which usually is bouncing our own heat back at us so that we don't realize how cold it is a few miles above our heads. This paint only works when it's facing the sky, hence its name, radiative sky cooling paint. Before going further, let's look at some of the results. This is a panel with a stripe of cooling paint in the middle. If I aim a thermal camera at a piece of plywood that has been in the shade, we can use this as our baseline reading of ambient temperature. And then if I take off this piece of insulating foam, we can see the cold stripe in the middle of my test panel where the paint has cooled it. Notice that this has a reading several degrees colder than an identical piece of plywood in the shade. Infrared temperature readings can suffer from calibration errors when measuring dissimilar materials, but because we are comparing the readings between two samples of an identical material, this is a very accurate way of measuring the difference in temperature between them. This is amazing to me, and you can push the temperature even colder by bringing the painted sample into the shade also, as long as it still has a clear view of the sky. Now, before anyone goes painting their whole house with this stuff, this is a relatively fragile coating, and it requires being covered by a plastic film to not waste its cooling potential on the outside air, as well as to stay clean. I think the best practical way to use this is not going to be as a typical exterior building paint. In the long term, we'll have to design various items and applications that are intentional about using a radiative coating effectively. I, of course, will be working on this myself, starting with the previously mentioned cooling panels. So now that you've seen the demonstration of how this paint works, buckle in, because inventing a recipe for a cutting-edge technology that's as easy to follow as something out of your average cookbook was not a straightforward process. So in my first video on this topic, we explored a version of this paint that used barium sulfate as the pigment. Barium sulfate emits infrared light that the atmosphere is transparent toward, and the best results that have been reported in scientific literature have used this as the pigment. But there are other options. Calcium carbonate is the most notable option because it is extremely common and cheap. You might know it as limestone, eggshells, the main ingredient in cured cement. I take a tablet of this occasionally to treat acid reflux. We couldn't hope for a more common and safe ingredient. So using calcium carbonate was my goal for this project. The challenges to make that happen, it turns out, were unexpectedly difficult, and I'll explain why in a moment. The YouTube channel Tech Ingredients recently made their own video about radiative cooling paint. They achieved an excellent result with the previously mentioned barium sulfate pigment, and their methods helped me to realize a few strategies that I had neglected to take advantage of in my own paint. In my last video, I knew that microspherical pigment was used for many cooling paints in various research papers, but I didn't properly understand why. I thought that spheres were maybe just a little bit better at reflecting light than other random shapes, and so I tried making barium sulfate microspheres for use in my paint, but they only made a tiny difference in my results. What Tech Ingredients helped me to realize is that the primary benefit of using spherical particles is not reflectiveness, but packing density. Here I have a jar full of ping pong balls, and you can see that there are large air gaps between them. When randomly poured into a container, the density of spheres tends to be about 65% of the container's overall volume, leaving 35% as empty space. 65% is actually pretty high for shapes that were randomly dropped into a container, which is an advantage of spheres. They tend to slip past each other and arrange into a dense configuration all on their own. Now, if we know what we're doing, we can make the density way higher. By combining small spheres with these larger ones, we can fill in the gaps. Now the space between ping pong balls is itself 65% full, bringing the total density in this container to about 87%. 13% is still empty space between the gaps in these now smaller spheres, but that 13% could again be filled with even smaller ones, then achieving about 95% total density. And you could keep going further. The only qualification to achieve this super high density is that each size of sphere must be significantly smaller than the one before it. If the spheres are too close in size, it can actually make the density worse, because the larger ones need to be spread apart in order to make room for the next size. Ideally, each step down in size should be small enough to easily flow through the gaps between larger objects without their having to move out of the way. A microscopic version of this is how you make a high-density pigment, which is what has been shown to give the best results in a cooling paint. It's easy enough to make microspheres in a variety of sizes from barium sulfate. That was dealt with in my first video, and to an even greater extent by Tech Ingredients. Calcium carbonate has some very different chemical properties. While there are many papers about making calcium carbonate microspheres, there are very few that talk about how to make them in a variety of different sizes. In the end, I found no published method that was suitable for easy at-home reproduction, so we're going to have to come up with something completely new. Each one of these pipettes represents an individual experiment in which I attempted to make calcium carbonate microspheres and control for their size. As you can see, this took me a while. To make calcium carbonate, the first step in all cases was to react sodium carbonate with calcium chloride. Sodium carbonate is sold as washing soda in just about every hardware and grocery store. But don't get it confused with baking soda. Baking soda, if necessary, can be converted into washing soda by heating it in an oven at 200 degrees Celsius for about an hour. But it's better to just buy pure washing soda to begin with. Calcium chloride, the other chemical in this reaction, is sold in 50-pound bags for several purposes, one of which is for melting snow and ice, and the other is as a painter's desiccant. Basically, this is a chemical dehumidifier. It pulls water out of the air. Pure calcium chloride flake is sold in many hardware stores for one of these two purposes, and it's very inexpensive. I've used this both to melt ice on my sidewalk and to quickly dry out my basement after flooding. The point is, both of these ingredients are common and cheap. Dissolving each of these chemicals in water and then combining them will form our pigment, calcium carbonate, with a byproduct of table salt, sodium chloride in solution. The result of this simple reaction will give us lots of random crystal shapes. If we're lucky, we might be able to find a few spherical objects in with a mess of other things, but very few. There are a few tricks we can use to increase our chances of forming spheres. Many papers suggest using very dilute solutions of the starting ingredients. Just a pinch of calcium chloride and sodium carbonate in whole beakers of water, and then combined with very fast stirring on a magnetic stir plate. This method does work about a quarter of the time. It's very unreliable, but at the right reaction temperature and stir speed, we can get spheres instead of random crystals. But one enormous problem is that because of the low concentrations of ingredients, you would need to mix gallons and gallons of water to make just a little spoonful of microspheres in the end. You also need to use high purity deionized or distilled water for these reactions, so it's pretty wasteful. If we want to make enough pigment for practical use, we need a method that can make microspheres in quantities like this. Big honkin' bags full that can make enough paint to cover a large surface. To make this many microspheres, the methods that use low concentrations of ingredients are out, which disqualifies about 99% of all the published research on this subject. One exception was this paper, which used fairly high concentrations of calcium chloride and sodium carbonate. And what really stood out was their use of sodium citrate, which for some reason helped in the formation of spheres. At first, I did not pay for access to read this paper, so just going off of what I could see in the abstract, I started playing with sodium citrate as an additive to this reaction. This was super interesting. Sodium citrate, it turns out, delays the formation of calcium carbonate. When you have a bunch of sodium citrate mixed in the same solution as the calcium chloride, when you then add the sodium carbonate, everything turns into a gel. It's really weird. Under a microscope, it looks like fabric. What's even stranger is over the course of the next few hours, you start to be able to see tiny spheres growing out of this fabric. It's like stars growing in a microscopic nebula. So this method worked. After about 12 hours, all of the gel was consumed as the spheres grew, and they all end up just about the same size. This was with approximately a molar ratio of all three ingredients. What I discovered is that by reducing the amount of sodium citrate, the crystallization reaction starts to go faster and faster. Its primary function seems to be as a delaying agent. At a certain point, around 20% of the original sodium citrate concentration, we stop forming spheres and start to get other crystal shapes. But the reaction is still delayed enough that we can place a drop on a microscope slide and observe the crystals forming in real time. So I definitely learned some interesting things as a consequence of this paper. I ended up purchasing access to the full text, but it didn't turn out to provide much additional help. The paper only made one size of sphere, and their discussion about the possibilities of why sodium citrate helps in the formation of spheres was not very conclusive. In any case, using sodium citrate allowed me to make microspheres with the most consistent results yet. This was a necessary step before I could move on to further experiments to hopefully learn how to control their size. Immediately upon my first successful results, I tried changing the reaction temperature to make smaller and larger spheres. That's how barium sulfate spheres are made into different sizes, but calcium is not so cooperative. The reaction only worked in a range between about 5 and 30 degrees Celsius, and the size of spheres was very inconsistent. The size definitely did not correlate with a change in temperature. Much of the time, no spheres were made at all, which was very confusing. I also attempted to change stirring speed, stirring duration, and the concentration of the reactants to see if any of those things would make a difference in particle size. Again, very inconsistent results. For most of these tests, I was using a molar equivalent of sodium citrate compared to the calcium chloride in the solution, which meant that the crystal growth was very slow. But this ratio had given me the most reliable results early on, so I stuck with it. This is one of my first tests comparing the size of spheres made to the amount of time the solution was stirred. You can see that right toward the end, at the 40-minute and 1-hour mark, that the size becomes slightly smaller, but it stays the same until then. My conclusion from this was that stirring time has some effect on size, but that it's not very effective. That was a bad conclusion. It took me way too many failed experiments before I came back and reconsidered that this early test should not have been ruled out. This mistake turned out for the best because I discovered more things in the meantime that helped refine the final process. One of the things I discovered is a way to make the starting solution self-purifying. One issue with crystallization reactions is that the starting solutions need to be super clean because any speck of dust or contaminant will nucleate the growth of crystals in shapes that are not the ones we're looking for. This is a particularly annoying problem when using calcium chloride because this stuff reacts with CO2 from the air to form calcium carbonate, the same stuff we're trying to make, but in a disorderly way that prevents the formation of spheres. When I dissolve this calcium chloride in water, you can see that the solution is not clear. This milky haze is made up of microscopic calcium carbonate crystals that have naturally formed as CO2 reacted with the chloride flakes while they were in storage. If I used this solution immediately to make microspheres, about half of the end product would instead be jagged, misshapen chunks. For a good result, you have to let this solution settle for about 12 hours before using it, and then very carefully pour the clean liquid off the top. All of this can be avoided by swapping sodium citrate for citric acid. Citric acid dissolves calcium carbonate, so we can see that if I take a little bit of citric acid dissolved in water and pour it into the calcium chloride solution, it turns crystal clear. Citric acid dissolves all of the contaminants that would prevent the formation of spheres, and it performs the same function as sodium citrate because it actually turns into sodium citrate as soon as it mixes with the other chemical in this reaction, the washing soda, sodium carbonate. We also get other benefits, like citric acid being a common item in grocery stores because it's used for canning. And because of its purifying effect, we no longer have to use high-purity distilled or deionized water. I tried tap water, water from an in-ground well, and even water from a dirty rain barrel, and it all worked just as well for making microspheres because of the self-cleaning effect of the citric acid. Now, eventually I made my way back to testing stirring time as a means of controlling particle size. The reason this did not work very well the first time is because I was using so much sodium citrate that it delayed the reaction to the point that the first crystals didn't even nucleate until at least the 40-minute mark. There's no reason to expect that stirring before that point would make much difference. One final paper I'll mention is this one. This is by far the best article I found that explored the factors that change the size of these microspheres. The authors used methods that I think add unnecessary complexity, but their conclusions were super helpful. First of all, they confirmed that temperature is not at all effective for size control, which was welcome confirmation of my own findings. Most importantly, and I'm embarrassed to have not realized this myself, this paper found that the most important factor that determines the size of the microspheres is the number of nucleation sites in the solution. I should have realized this really early on, as soon as I saw the spheres growing in the fabric-like gel under my microscope, and how that gel was consumed as the particles grew. Think about it. If you only have one sphere growing in this whole patch of gel, it's going to get enormous because it has so much material surrounding it that it can use to grow. On the other hand, if spheres start to grow from a whole bunch of nucleation points in the midst of this gel, they're going to start stealing resources from one another. And by the time the crystal feedstock is depleted, they will still be quite small. It's a very simple concept, and as soon as I read this paper, I knew why my first stirring tests had not worked, and the solution to my problem. I need to be stirring the solution during the nucleation stage of the microspheres. The agitation should create more nucleation points, and the more I stir during this stage, the smaller the resulting spheres should be. The other thing I can do is use less citrate so that the reaction occurs faster and I don't have to wait an hour before the stirring starts to become effective. I did a fresh batch of tests now that I switched in the new ingredient, citric acid, and found an effective mixture to reliably make spheres. I'll explain the details of that mixture in a moment. Here are the results of my first stirring test. For the first time, I was able to control the size of my microspheres very reliably. And even better, we know why this method works. If I want even smaller particles, I know the key is to use even more agitation, generate even more nucleation sites during the initial stages, and we'll get yet smaller spheres, perhaps even down into the nanoscale. Well, that was a deeper dive than I expected to get into, but now you know some details about what we're actually doing here. Actually, I haven't even explained why I think spheres are formed instead of other shapes. There's a lot of technical information that maybe I'll talk about in a supplementary video. It's about time I present the final recipe for making this pigment. To make everything as easy as possible to follow, all the ingredients are dissolved in a 1:10 ratio with water. The basic mixture, which can be scaled up or down, is 20 grams of sodium carbonate dissolved in 200 milliliters of water, 10 grams of calcium chloride dissolved in 100 milliliters of water, and 3 grams of citric acid dissolved in 30 milliliters of water. The mixture of citric acid is combined with the calcium chloride solution, which causes it to go clear as the acid dissolves any impurities. Now, the liquids in these containers must be between 10 and 20 degrees Celsius before mixing them, ideally right in the middle at 15 degrees. A small kitchen thermometer is perfect for measuring this, and the chemicals we're using are not at all dangerous for food contact, so if necessary, you can cool the solutions in a refrigerator. Once the liquids are within the 10 to 20 degrees Celsius boundary, all we need to do is mix them together with vigorous stirring. I used a magnetic stir plate for all of my earlier experiments, but I think a better tool to use is a blender, particularly because this will be useful for a second purpose later in the paint making process. You can also get these super cheap at second-hand shops, often for less than $10. The calcium chloride and citric acid solution goes in first, and at this point we need to be ready with a timer. Side note, because this blender holds a lot of liquid, I have tripled the basic recipe size so that it fills more of the container and will not splash as much when I turn the blades on. Now we can set this blender at the lowest speed, and when ready, remove the lid and pour in the second solution of sodium carbonate. Right then, we start the timer. The largest sphere size will be made with about 1 minute of blending. Here again are the results from my tests with a stir plate. A blender is much more powerful, which means you can expect the particle size to shrink even more dramatically for each increment of stirring time. I'll stop the blender after 1 minute for our first batch of the largest particle size. For the time being, this mix can be poured into a separate container while we get ready for another batch. Cleaning between batches is really easy because our ingredients are dissolved by acid. Put the container back on the blender, pour in a splash of vinegar and some water to dilute it, and turn the blender on. Everything will be clean and ready to use again within a few seconds. Now, our largest microspheres are starting to settle out in this container. For a high-density pigment, we now need a smaller size to mix with them. If we go back to the percentage bar I used earlier when talking about sphere packing, we can see that the largest size takes up 65% of the total volume, and the next size takes up 65% of the remaining volume. If you ignore the empty space and just look at the ratio between these two parts, you can see that you only need about 25% small particles compared to the volume of the larger ones. In other words, you need 3 parts large particles for every 1 part of a smaller size. So to make a whole bunch of pigment, we can repeat what we just did 2 more times so that we triple the amount of these large microspheres. And then we run 1 more batch and make that one a smaller particle size by blending it longer, for about 5 minutes. When the 4 batches are combined, it will be 3 parts large spheres and 1 part small to match the percentages of the scale. For the best results, you can go 1 step further and increase the density to 95% with a 3rd size. The quantity should again be reduced to 1/3 of the previous batch. This mix should be blended for 8 to 10 minutes, which brings you well into the range of making nanoparticles. These are very small. So now I have 5 total batches, and these 3 contain my largest particle size. This one is a medium size, and in this container are the very smallest microspheres. Most of them have already settled to the bottom of the first 3 containers, so now we just need to wait about 15 minutes for these ones to do the same thing. Once settled, the clear liquid can be poured off the top as waste. This contains lots of dissolved table salt, sodium citrate, and excess sodium carbonate, all of which is non-toxic, but we don't want it in our final product. The microspheres should then all be combined into one single container and topped off with fresh water. Over the course of a few minutes, everything will settle out again, so the top can once again be poured out as waste and refilled with more water. We'll do this 2 or 3 times to remove as much of the dissolved salts as we can, and then it's time to filter and collect our finished pigment. Filtering nanoparticles can be pretty difficult because they either pass through or clog most filter paper. Fortunately, I've found an easy solution. We will use capillary action to suck the water out of these particles through an ordinary piece of printer paper. First step is to take one of these disposable aluminum bread trays, cut an opening in the bottom, and line the tray with a paper towel. Now insert a piece of printer paper, carefully folding it to line the sides. You don't want any part of the edge to be too low in the tray or the liquid will overflow. And this is our filter. We can pour in the finished pigment and watch as the water drains out. Because of the paper towel that lines the bottom of the tray, water is pulled through much more quickly, and this only takes about 15 minutes to drain. The paper becomes very fragile when wet, so don't stick a spoon in here and stir the pigment around, or you could cause a tear when you touch the sides. Once fully drained, I recommend refilling this one more time with distilled water to pull out the last bit of dissolved contaminants. Finally, the whole tray can go right into a toaster oven set to stay on at about 200 degrees Fahrenheit or 100 Celsius for about 2 hours, with the door open to let out steam. And here is the finished pigment, dry and on the filter. This can be carefully crumbled and poured into a plastic bag for storage. I recommend wearing a dust mask for this step, or doing it outdoors. Pure calcium carbonate is not particularly dangerous because your body chemistry can actually dissolve it, but this powder is really dusty, and a mask is an easy precaution. That's all there is to it to make this high-density cooling pigment. It's about a 5 or 10 minute process to measure the ingredients for each batch, get them blended, and then clean out the blender for the next one. About a half hour in total to get all the batches made for each particle size, and then the settling, filtering, and drying process can be done in the background while you work on other things. It really doesn't take a lot of effort, and if you want to make more, just switch in some bigger equipment. You can make 4 or 5 kilograms at a time with a paddle mixer and a garbage can. By the way, you can expect to end up with about 8 grams of calcium carbonate microspheres for every 10 grams of calcium chloride used in the starting ingredients. That's about a 90% yield compared to the theoretical maximum, which is pretty good. So let's look at this under a microscope, and hopefully we'll be able to see how the particles come together in a high-density configuration. And that's exactly what we see. All the gaps between large objects are filled in with smaller ones. That means that when we're counting on this pigment to radiate its heat away as a particular wavelength of infrared light, every microscopic area of our paint will be jam-packed with particles that can do so. Very little wasted space between them. So this high-density pigment, which can now be easily made at home, is by far the most important ingredient in a sky cooling paint. It's possible that this could be mixed with all sorts of different off-the-shelf products to make coatings that can reach subambient temperatures. That will require further testing. As it stands right now, I only know of one mixture that definitely works, which uses the same method detailed in my previous video on this subject. That is, using a base of dissolved acrylic with a special effect that allows the finished coating to scatter light using the same properties as snow. To make the liquid base for our pigment, I start with a beaker of acetone. For every 110 milliliters of acetone, we will add 12 milliliters of water. Make sure this is fresh acetone, not more than a few years old. Otherwise, it will already have absorbed water from the air, which will throw the measurement off. With the water mixed in, I then add 10 grams of acrylic and seal the opening tightly with a piece of foil. Last step is to mark the beaker so you know exactly how full it is at the start, so if any acetone evaporates, you can refill it to this line. The acrylic pieces are literally shards of broken acrylic windows, plexiglass. You can get scraps of this for free if you call a few hardware stores that do glass cutting, because inevitably they end up with thin little strips left over from cutting acrylic windows. Usually these just get thrown away unless someone like me shows up and asks to have them. The acrylic will slowly dissolve in the acetone over a few days, but you can shorten this process to a few hours if you put it on a hot plate at a really low temperature, about 110 Fahrenheit, 43 Celsius. By using a water bath, it makes it much easier to hold the temperature steady. Now, if I had dissolved the acrylic in pure acetone, when it dries it would once again turn clear. However, because I added water to this mixture, the water is going to stay behind as tiny droplets in the plastic until after the acetone evaporates. The water will evaporate later, leaving behind millions of tiny hollow spaces in the acrylic that scatter light. This makes the formerly transparent layer of plastic transform into a very bright white, using the same effect that makes snow appear white, even though snow is made from transparent ice. This will give us a free increase in the brightness of our paint, and the effect works even better once we start adding pigment. This also increases the flexibility of the final coating, because it gives the paint a microscopic foam-like structure that is able to more easily deform without developing cracks. The application method that I currently use for this paint actually does not work if water is not added. Pure acrylic buckles and peels in giant pieces as it dries, but the mixture with water holds strong. When I make this paint from scratch, I usually prepare the acrylic mix first, so that it's ready to use by the time I'm finished making the pigment. If you do the math on this mixture, there's about 1 gram of acrylic dissolved in every 12 milliliters of liquid, to which we will need to add 7 grams of pigment. This mixture can of course be scaled up, so since I have 120 milliliters of the acrylic mix here, I will need 70 grams of the pigment. For 1.2 liters, you would need 700 grams, which would make about 2 liters of paint in total, because the volume increases when the pigment is added. One of the best things about using this Microsphere pigment is that it mixes into a paint really easily. You don't have to use any power mixing to get this to distribute through the liquid. It can be stirred in by hand. Now, if you washed the pigment extremely well during the settling and filtering process, there should be no clumps that take more than light pressure to fully disintegrate. But chances are you may not do a perfect job filtering, which will result in hard clumps distributed throughout the powder. These are caused by water-soluble contaminants like table salt or leftover sodium carbonate that was still in the powder when it went into the oven to dry. When the water evaporates, these contaminants crystallize in between the microspheres, gluing some of them together. The good news is that these are really easy to deal with using the blender that made this pigment in the first place. The powder is put right into the blender dry so that the blades can break up any water-soluble crystals and the clumps will not be able to reform. You want to be careful doing this for the sake of the blender, because without liquid the blades can easily overheat and damage the seal that keeps this container watertight. Only blend for about a minute at a time on low speed, and then let the container cool off before turning it on again. After 4 or 5 cycles, the powder should be completely smooth and ready to use. The blender, by the way, won't cause any damage to the microspheres. Compared to their microscopic size, the blades in this are about as blunt as my forehead, not nearly sharp enough to slice anything in half. So now the acrylic mix is ready, the pigment is lump-free, and we can mix these together. 7 grams of pigment for every 12 milliliters of liquid. This should only take about 30 seconds to a minute of stirring before the microspheres are evenly distributed and this starts to look like paint. The acetone in this is going to evaporate really quickly, so as soon as I'm done mixing, I'll cover this with my foil again until I'm ready to use it. While I mix this, we're going to take a pause here for this video's sponsor. Well, with this project requiring so many variations on experiments, I found myself wishing I had some basic programming skills to help analyze the data. My younger brother is actually a professional physicist, and he's told me a few times that I would benefit from learning the programming language Python. So I've finally started doing that, using a course on Brilliant.org. Brilliant is seriously the best for learning math, science, and computer science because their courses teach through interaction. You get to play with the problems on screen in a way that helps you to understand a subject from the inside out. It prevents a common problem that I've experienced in my own education, where I learn a new subject, but I don't really understand why one solution works and another fails. That seems like a really shallow education. I want to know why something works, not just that it does. This is where Brilliant really shines and why I've been happy to have them as a sponsor for over 5 years. This intuitive hands-on problem solving that they work into their courses is excellent at getting that deep understanding to sink in. It's fun too, and really satisfying to learn a new skill. Brilliant has thousands of lessons to choose from. You don't need to just be interested in programming or math. You can check out everything they have to offer for free for a full 30 days by using my link brilliant.org/NightHawk. And if you like what you see, you can also get 20% off an annual premium subscription by using that same link. Isn't that right, Mose? He agrees. Now, this is where I need to confess that calling this mixture a paint is playing pretty loose with the definition of the word. It doesn't spread well with a brush, and I've yet to perfect a way of applying this with a paint sprayer. The closest I've come to spraying this on is with a hand-squeezed chemical spray bottle, and then it comes out less like a spray and more like coarse drops, which self-level on the surface. This actually works reasonably well, and the liquid has enough viscosity to stick even to non-level surfaces. You can see that I was able to paint an aluminum tube with this method for an experiment that may or may not make it into a future video. Because of the water included in this coating that gives it a foam-like structure, it's able to be applied in extremely thick single layers, even up to several millimeters at a time. When it dries, it will shrink down to about half of its thickness. I think half a millimeter is probably close to the ideal thickness to aim for in the dry state. You won't hurt anything by applying a thicker coating, but then of course it's a waste of materials if you could have spread it over a larger area. The most reliable application method that I've found so far is to use a large syringe. First, suck up the paint. Shake the liquid down into the base of the syringe so you can purge any air bubbles from the tip, and then extrude it line by line on the surface. You do get little ridges and uneven thicknesses between lines, but those get better with practice. It seems like this would be a really silly way to apply a coating to a large surface, but the more I try it, the less impractical it feels. You can buy really big 300 milliliter syringes, which would hold plenty of paint for a very large cooling panel. It would be better if we could find a flat tip for these syringes so that you could cover a wider area with each pass. And on that note, I had a different idea, which was to use a piping bag. These of course are made for applying frosting to a cake, and you can get super wide nozzles for the end of the bag. The only problem is that you have to be much more particular about the consistency of your paint, because if it's too thin, it will pour out and make a huge mess. At the right consistency, this works really well to lay down wide sections at a time. So those are a few ideas that I have successfully used to apply this coating so far. I obviously hope to develop a more standardized and convenient application method in the future, but at least we have several options in the meantime that definitely work, even if they're a little bit strange. Developing the calcium microsphere recipe is an enormous step forward in terms of making sky cooling paint accessible for the average person. I think the pigment made in this video is as good as anything available, even to scientists in commercial laboratories. But that does not mean there's no more room for improvement. I've barely scratched the surface of what kinds of sealants, silicones, adhesives, polymers that this pigment could be mixed with and still achieve the same or even better cooling. There are endless experiments to try. And now that you all know how to make high-performance pigment, I hope to see a few more people testing their own ideas. If you do, take a video, email me a link, and I'll feature it on my channel homepage in the video response playlist. If this video seems like a valuable contribution to the things you enjoy, consider supporting my channel on Patreon. Most of my videos will not be this long or this in-depth, but the more people who back these projects with a fixed contribution, the less I need to worry about spending weeks at a time making fancy dust, and then giving away my fancy dust recipe for free. Fortunately, all of you have been really good to me by watching these videos over the years, keeping my views up so I can continue to get sponsors, coming back even when I've been gone for months due to sickness or failed projects. Thank you for that, and thank you for continuing to leave me comments. To this day, I still read all of them on all of my videos. It's not as hard as you might think. It takes me maybe 10 minutes per day. I really enjoy hearing from you. Thanks so much for sticking around to the end. Thanks for watching. I'll see you next time.